Hello, welcome back for lesson 10.2. We are going to put into practice what we learned from 10.1. Once we check to see if there is a significant relationship, linear relationship between two variables, we can use that regression equation to make some predictions about the data. So this is just a reminder of how we entered our data into a table, into Desmos, and then we use this equation, depending on the table column numbers, to get our linear regression. So let's just jump right in here. So it says that the data show the final exam grades for 16 randomly selected students taking both a college algebra course and a statistics course. Use the college algebra scores for the independent variable and the statistics scores for the dependent. So we're first going to go to Desmos and find the equation of the regression line. And then we're going to do some predicting. Let's find the statistics score when the college algebra score is 80. So let's go ahead and go to Desmos. And look at this. So here is the data. And there's definitely a significant relationship. You can see the R is 0.9083. And if you look at the table, let's just make a comment here. R is equal to 0.9083, and it is bigger than, if we go to the p-value table, and there are 16 pairs, so that means degrees of freedom equals 16 minus 2 equals 14. So if we look at 14 under 0.05, it's 0.497. And so because the R is bigger than 0.497, we can say there is a linear relationship. And now, since we know there's a linear relationship, we can now use this equation to make some predictions. So we are going to write on our paper y equals, and then our slope is 0.69. We'll just round to 2 decimal places. So here's our slope in our equation that it modeled for us. And then I'm going to round my y-intercept to 1 decimal place. So y equals 0.69x plus 27.0. And then letter B says, find the statistics score when the college algebra score is 80. So what we want to do is we're going to go to our graph. I'm going to zoom a little bit so I can see my x-axis here. And so this is 50, this must be 60, 70, 80. So I'm just going to go up to 80. You can grab your graph the linear model that you created. That's what this green line is the model. And we can go to where x is 80. You can move it there. That's one way. And so that gives us a statistics score predicted of 81.8. Another way to do that would be, you could just say x equals 80, and it's going to draw the line at 80, and then you can just click on that dot intersection, and it will give you the y value that goes with that. So I'm just going to go back and share my paper so you can see what I've written down. So this is the regression model that it came up with, and then we used when x is 80, we found that we would predict that their statistics score would be 81.8. So it does show that when you have strong algebra skills, your statistics skills will be higher as well. So let's go to example 2. Example 2 is going back to data that we looked at in lesson 10.1. So when we had the age of drivers and the number of accidents they had, we're going to go back and look at that regression line, and then we're going to predict the number of accidents when a driver's age is 30. So when X is 30, we want to know what Y is. So we're looking for Y equals, and then we'll find that. So let's just go back to our Desmos from 10.1 here. So I'm just going up to the accidents tab, and I'm going down to the equation, and it says the slope rounded to 2 decimals is a negative 0.18, and the y-intercept is 9.0. So the equation is y equals a negative 0.18x plus 9. And we want to know when x equals 30. Oh, so you know what we have to do is we have to go back down and turn off this other data here, because the computer is confused, and I can see why. There we go. So here is our accident data again. So again, I can just grab my equation. Oh, and right there it is. So when an age of a driver is 30, it looks like they're expected to have about 3.6, so between 3 and 4 accidents. And let's look at our last example here. Our last example is these data were obtained for the years of 2009 to 2014 and indicate the number of fireworks in millions used and the related injuries. Predict the number of injuries if 100 million fireworks are used during a given year. So we're going to go and look at this data on the scatter plot. Even though I don't have a formal test, hypothesis test here, we're going to look at the R and just compare it to the table 8A. And we can just get that critical p-value from table A8. There are 1, 2, 3, 4, 5, 6 pairs. So we're going to go to that table, and it will be 0.05 and 4. So we're looking at 0.811. And we're going to compare that. So let's just go to Desmos here. And I'm going to turn these off. And that, and then here is our fireworks. So here's our fireworks data. Let's go ahead and hit the zoom. So the fireworks data does not look like there is a good fit. Notice that the R is, the absolute value is 0.2602, which is less than the critical p-value. So not necessarily a linear fit, but let's go ahead and write down the equation. Y equals, the slope is a negative 18.10x plus the y-intercept is 13,424.8. And we wanted to predict, it says, I'm just going to zoom out here for a minute, when there are 100, which is interesting because we really should never be predicting outside of the data we have. And because 100 million fireworks is less than what we have, the lowest one we have is 186 million, but we're going to go ahead and just click on it and see what the prediction is. And I've got to get it right there at 100. Finished type X equals 100. There we go. Now I can click on it. So it looks like they're predicting when X is 100, they're predicting about 11,614.3 accidents. But we can't really use this as a predictor because there isn't a significant relationship. So let's just go back and acknowledge that on our paper here. So because of this, there's not a significant relationship. So important things to consider, especially before you complete the homework and take the chapter 10 quiz. Don't forget to reach out if you have any questions. And have a blessed day.